So our second speaker is Vahan Nersesyan, and he will talk about ergodicity via controllability.
Okay, thank you very much. Thanks to organizers for the invitation. So I will speak about the problem of ergodicity for randomly forced PDEs. More precisely, I will try to explain how controllability can be used to derive ergodicity results. So this talk is based on joint works with Sergei Kuksin and Armen Shirikian. So let me start with two examples for which this approach can be applied. These are Navier-Stokes and complex Ginzburg-Landau equations. Both are coming from the hydrodynamics. So Navier-Stokes is considered in dimension 2. Complex Ginzburg-Landau has a quintic nonlinearity and is considered in dimensions 1, 2, or 3. So in order to have globally well-posed that dynamics, the noise will be eta, which will be additive. And so before explaining our assumptions on the noise, I will recall you some well-known facts from the literature. So in the literature, the problem of ergodicity is mostly studied in the white noise situation. And let me say from the beginning that white noise, so applied to the complex Ginzburg-Landau with quintic nonlinearity, there is no any result, simply because the nonlinear term is too big for that type of noise. So we will be in the case of Navier-Stokes with white noise for the literature review part. So the noise is white means simply that it has this form where Bj are some vectors that are square summable and non-zero. So eta j are independent standard Brownian motions, and you have the Fourier basis of sine and cosine functions. So the j here, this is what I will call in what follows Fourier modes. These are vectors of integers. And capital I here is the set of all Fourier modes that are perturbed by the noise. So in some sense, the larger is I, simpler is the ergodicity problem. Simply because at some point in the proofs, we are going to replace the noise by a control. So more noise you have, seems that later you will have more control. So simpler will be in some sense the problem. Okay, so some results from the literature. Of course, the literature is really very rich on this topic. I give here only some results that are related to this talk. So the first result of ergodicity is obtained by Flandol and Maslovsky in the non-degenerate situation. Non-degenerate means that all the Fourier modes in the equation are perturbed, which means that I here equals to Z2. They obtained existence, uniqueness of invariant measure, and mixing without rate of convergence. Then there is this second family of results where exponential rate is obtained under weaker condition on the noise. So here it is proved in the final form, the result here says that for any viscosity, there is an integer n depending on the viscosity, so that if you perturb the first n Fourier modes, then you have exponential mixing. And n nu goes to infinity when the viscosity goes to 0. So this result can be applied in the case of torus or a bounded domain with Dirichlet boundary condition. And then Herrer, Mattingly, and Pardue proved that this result remains true in the periodic setting, remains true. Also, if you perturb only very few Fourier modes. for example, only 4 appropriately chosen Fourier modes, you perturb by a noise, you get exponential mixing. Okay, to learn more about this stuff, or to have more references, you can go to the book by Sergey and Armin. So, so our project with Sergey and Armin was to understand what happens if the noise is still degenerate, but has not this Gaussian structure. It is not a white noise. So in their proof, Herrera, Mattingly, and Pardue use in a very essential way the Gaussian structure, because they use this Malyavin calculus, the integration by parts formula of Malyavin calculus. And so if you work with a non-Gaussian noise and under very mild assumptions on the density, on the regularity of density, you don't have any more such formulas. So what we do in our approach, we use in a very essential, in a very important way, the equation, the deterministic part of the system. Okay, so what we are going next, so I will explain which are the controllability properties of the equation that that imply the ergodicity results for the system. Okay, so both examples that I gave, both examples can be written in this form. So let us forget examples and from now on discuss this abstract setting in a infinite dimensional Hilbert space. So in the equation, we have some linear part L, which is dissipative, a nonlinear part B, which is in concrete cases a polynomial in U and its partial derivatives. And then there is the noise. There is the noise, which is additive here, and it has the following form. So eta is a sum of characteristic functions of intervals k, k plus 1, and some processes, eta k, some shifted processes. So this eta k takes values in E, this space E. And so to understand what does it mean, it is really easy. So let us assume that k equals to 0. Then in this sum, you have only one term, the first one. Okay, so you have a process eta 0 that perturbs the equation. It perturbs on the interval 0, 1, and then at time 1, it disappears. It is replaced by another process, eta 1, that is independent from the previous process, but has exactly the same law. So it perturbs the equation from time 1 to 2 and disappears at time 2, and so on. And what is important is that this process takes values in a finite dimensional space H, which in the case of Navier-Stokes will be 4-dimensional. Okay, so so we need to assume something more about etas. So before giving you the assumptions about this sequence of eta k, so let me make a simple remark that in fact the structure of the noise allows us to write the trajectories as a discrete dynamical system in the following way. So if you restrict the trajectories of this system at integer times, then you will have the following very simple formula. Okay, at time k, the value of the trajectory is completely determined by the values at time k minus 1 and the process that perturbs the system on the interval k minus 1 k. Okay, so where this mapping S is deterministic now. It is the resolving operator of our equation. So the first argument is the initial condition, the second argument is the process. So the value of S over this couple is the value of the solution at time 1. Okay, so this is a very convenient form of writing this trajectory. Then we assume two things about these perturbations. Until now, there were no assumptions. So the assumptions are the following. The noise is bounded and decomposable. What do we mean by this? Boundedness simply means that the norms of these processes are almost surely bounded by some constant. And then decomposability means that there is an orthonormal basis in our noise space, E, such that eta k can be decomposed as an infinite sum in this basis of this form. So Cj are some square summable constants. Cjk are IID random variables which have density with respect to the Lebesgue measure, a density which is only C1 smooth and positive at 0. Okay, so we will have these two assumptions on the noise. Of course, this assumption of boundedness does not allow to include some unbounded noises like white noise or other unbounded noises. So this is purely technical assumption which simplifies some computation, some estimates, but there are all the reasons to think that this condition can be relaxed. But this is not done for the moment. So we don't need any more structure from the density. You see, no more regularity, no formula. Okay. Then this is the assumption on the noise. There are assumptions, of course, on the equation too. So it is convenient to formulate the assumptions in terms of this operator S. This is simpler. So we will assume three conditions for S. The first one is a regularity assumption, which says the following. The operator maps to some more regular space V, which is compactly embedded into H, into our main functional space. So in concrete examples, H is always L2, a Lebesgue space, and V is a Sobolev space. So since these are parabolic equations, of course, you have regularizing effect, and of course, you have compactness of the embedding of Sobolev space into H because it is a bounded space. We are working on a torus. Then there is analytic dependence on the noise. The solution depends analytically on the noise. Again, there is no any restriction to assume that because the nonlinear terms are polynomials. So in that setting, it is always true that there is an analytic dependence on the source term. The second condition is less generic. The first one is quite generic. The second is less generic, but simple to verify, to check for concrete situations. So for Navier-Stokes and Ginzburg-Landau, to check that the solution goes exponentially to 0, it is just very simple. You just multiply equation, you integrate by the unknown, you integrate by parts, and you have this. So you have 0 instead of the noise, then the solution goes exponentially to 0. So in particular, this assumption means that there is only one steady state for the equation. This is not generic assumption. The generic assumption would be to have finitely many steady states. And in a minute, I will give another abstract result which treats that case too. So the first two conditions are very easy to check in concrete examples. All the difficulty is in the third condition, the approximate controllability of the linearization. So what does it mean? This means the following. You take the derivative of S with respect to the noise. Then you obtain a linear operator that goes from the noise space to the fuzz space. So the assumption is that this linear operator has a dense image. And it has dense image for not any value of eta, but for almost any value. So it is written that this property holds with probability 1. Okay, so and it is important to assume that it holds with probability 1 because on some zero set, on some singular set of probability 0, it happens, and in concrete examples of Navier-Stokes and Ginzburg, it happens. There are trajectories, there are controls, so that this linearized system has not dense image. Okay, that it is, one can construct it by hand. It is not complicated, but what is important is that the measure of such singular set is 0. So under these three hypotheses, we have exponential mixing. So how we apply this? How we apply this result in the case of Ginzburg-Landau, for example? How can we apply? So we take this equation. The right-hand side is exactly what I have described above, with H, the finite dimensional space, given by sine and cosine functions. And I gives, as I told you, the Fourier modes that perturb the noise. We assume that 0 also belongs to this, and it is important. So there were three conditions. The first two conditions are always true, but to check the third condition, you see, in the third condition, there is the equation hidden in S, and in fact, there is also the noise hidden in L. So this assumption is an assumption both on the equation and on the noise. Okay, so in fact, to be able to check third condition for concrete examples, we need to add some hypothesis on the noise. This is what to be called observability hypothesis. Observability hypothesis means exactly the following. It is related to a control theory. It says exactly the following, that a function in this space is called observable if for any smooth coefficients depending on time, you compose this sum. The sum equals to 0 implies that the coefficients A, these three coefficients, are identically 0. So what we do next? So the theorem for Ginzburg-Landau looks as follows. Assume that eta, our noise, is bounded, is decomposable, and almost surely observable in the sense of the definition that I gave. Then the equation is exponentially ergodic if I is a generator. Okay, I, the collection of Fourier modes, correction of vectors, is a generator. Generator simply means that the linear combination of its vectors with integer coefficients gives all the Z3, because I formulate the results here in three-dimensional situation, gives all the Z3. The simplest example would be I equal to this collection. So you take 0 and you take the vectors of the standard basis. And then you will have a 7-dimensional space. 7 because you will have a sine and cosine function for each of these three vectors and one constant from it. So this is how looks the theorem for Ginzburg-Landau. So, so what happens if the nonlinearity is more general? What happens in the generic situation? One example for which the conditions of the previous theorem are not satisfied. Look, let us take a general polynomial B. Then there are many stationary solutions. So if you choose the principal coefficient of this polynomial positive and the degree you take an odd integer, then the equation is globally well posed. Okay, so in this situation we can use, when we have a multiple equilibrium state, we have another theorem which has three conditions. The first and third conditions are identical to the previous ones. The second one is much weaker. This is a controllability condition, and it is much more difficult to check in general, in the sense that you need to prove here that there is a point in the space which is accessible from anywhere with controls using only the Fourier modes of the noise. Okay, you are allowed to use only, in the case, only few 7 Fourier modes to control the equation, an infinite dimension equation. So it is not simple. But we have a paper on that. This is a paper on geometric control theory, which allows to derive such results for any polynomial. Okay, so it is hard to do, but it is true for any polynomial nonlinearity. And the result reads as follows. If you have these 3 conditions, then you have mixing. So we lose the rate of convergence, okay, because we have weakened a lot the hypothesis here. So if you want to learn more about the proofs, about the examples, you can read in our papers. So in the first one, we consider Navier-Stokes equation. In the second, this parabolic equation with polynomial nonlinearities. And the third paper is a control theory paper where we check this second controllability condition in the second theorem. Okay, thank you very much.